We'll be working on 5.5. I call it A, which is just a title I made up of derivative of logarithmic functions. So the first little part here, you can actually see how the log functions that we worked with in the past look like and how we can manipulate it so in the properties. So I'll leave that to you to look over at your leisure. What we're going to focus on primarily right now for this lesson is what the derivative of ln of x looks like. So when we have the basic ln of x, derivative of ln of x itself is just going to be basically 1 over x. That's the most basic one you can get. When we have, and it just goes through the proof, you can look at the proof for yourself as well. When we have ln of a function of x, that's supposed to be down below. It's not supposed to be that way there. Fix it up. This is really supposed to be f of x. All right. Basically, it's going to be the same thing. It's going to be 1 over f of x times the derivative of f of x. So that will give us our new form that we need over here. The best way to kind of figure this out is really to jump into the lesson. So let's try and do some examples. So for the first one, it says differentiate and simplify. So I just have to keep in mind that there's going to be a product rule in here. So I'm going to take the derivative. So I'm going to call this f prime of x, just so we know we're taking this derivative. And what I'm going to do is take derivative of the first part, which is going to be the x squared, which is really 2x. And I'm going to multiply that times the ln of x. Times the ln of x. And I'm going to add that to my x squared times derivative of ln of x, which is going to be 1 over x. Now, the x can cancel out with that x squared over there and get simplified. And we're going to try and simplify this a little more and put it into simplified factored form. So if we carry this calculation forward, it'll be a lot of canceling. Hopefully it'll happen, right? And I know I can factor out an x, and what's left is a 2 times the ln of x, and plus 1. So if I expand it, I should get something that looks like the top part, right? So if I expand the x in, I got 2x ln of x, and multiply, I get that lonely x at the top. So we're good. For part B, again, I'm going to call it f prime of x, just so we have something to tie it up into. It makes more sense for us. We can use a couple of rules. We can use the quotient rule. So I'm going to use that right now. So I'm going to take the derivative of ln of x. So ln of x, derivative of ln of x is 1 over x times the denominator, which is x. Subtract ln of x times, sorry, I keep on doing that with the ln of x, times derivative of the denominator, which is 1, and that's all over x squared. And we can simplify this a little bit, right? We can cancel out those 2 x's over there. And anything else we can do? I think that is going to be it. So when we simplify this, we're going to get f prime of x is equal to 1 minus ln of x over x squared. Excuse me. Now we're doing e dx as well. So how does that going to look like? Well, I got to remember that when I take derivative of e to the exponent x, it's e to the exponent x times derivative of the function. So in this case, it was x. So let's see what this looks like. So our f prime of x is going to be equal to derivative of e to x, which is e dx, times derivative of x, which is 1, which I'm not going to show, times the ln of x, plus e dx, times derivative of ln of x, which is 1 over x. If I try and simplify this, and see what I can factor out, I can factor out an e to the x, and what I have is ln of x plus 1 over x. And that's as far as I probably can go with that. Excuse me. For the next part, again, call it f prime of x. And basically, anytime you take the derivative of a ln function, it's going to be 1 over the function itself. So it's going to be 1 over x cubed plus x squared times the derivative of the function itself, which is 3x squared plus 2x. And if we put this together, what's going to happen, I ran out of space, so I'm going to put it over here again. What's going to happen is we're going to get f prime of x is equal to 3x squared plus 2x. Now in the denominator we have x cubed plus x squared, Or we have f prime of x, which is equal to, I'm going to factor out an x, and we get 3x plus 2 on the numerator, and on the denominator, we're going to factor out x squared, and we get x plus 1. And we can see that the x on the numerator cancels out with x in the denominator, and our final answer will be f prime of x is equal to 3x plus 2 over x times x plus 1. Excuse me. For part E, really what I'm going to write this as something a little more different, because this is going to be kind of complicated to work with. I'm going to use the log and ln properties. So I know that this is equivalent to the ln of x minus 1, subtract, because it's a quotient, the ln of x plus 1. Now when I take its derivative, it'll make my job a little bit easier. So the derivative of ln of x minus 1 is 1 over x minus 1 times derivative of x minus 1, which is basically 1, so I have to include that. Subtract 1 over x plus 1 and times derivative of x plus 1, which is 1, so we're done. So we can cross multiply and simplify and all that kind of stuff if you want. I'm just going to leave that for now. You can do that on your own. The next part, well, I'll sign the homework. I know I'd sign a different homework, but I'll put the homework for this what it was supposed to be. For the next part, we're going to be taking derivative of logs. And from this point forward, I don't want to see derivative of logs. We're actually converting to lns, right? So let's think about this. Really, this can actually be expressed as the log, if you remember, log of x over the log of b. And they share similar properties. So I'm going to kind of make a comparison as being the ln of x over the ln of b. So when we look at this here, we can actually see how we actually derived the ln of b times the 1 over x for the first derivative. So the forms we got to keep in mind, again, this one belongs to this, and this one belongs to that. And of course, the other one's written in a different format, but the same calculation. So the best way of actually understanding these formulas is to dive right in. So what I'm going to do is I'm going to do the log of x. And again, I'm just going to call it f prime of x just for simplicity's sake. And we know that the log of x, then really that's a base of 10, right? So we know it's a base of 10, so it's going to be 1 over x ln of 10. So again, that would be the same thing as saying, if you want, that's the same thing as saying the ln of x over the ln of 10. So ln of 10 is a constant. We take out the constant, take the derivative of ln of x. Let's try part B. Part B, again, I'm going to write this slightly different. I'm going to say that this is equal to x squared ln of x over ln 3. Or that's equal to, if you want to consider it as being 1 over ln of 3, which is my constant, times x squared ln of x. So if I take its derivative, what's going to happen is I have the constant I can take out. Right? I have the 1 over the ln of 3. And now I can take the derivative of x squared, which is 2x, times ln of x, plus x squared times 1 over x. And we've seen that before. I ran out of space, I apologize. And we can cross out the x's there, and we can factor out one of the x's. And our final answer, I'm going to squeeze in someplace here, is going to be equal to, well, we have our x going to factor out, and we're left with 2 ln of x plus 1 all over ln of 3. And let's try C. So for C, that's the same thing as saying, really, the ln of x squared plus 1 over the ln of base 10. All right, so now if I take its derivative, the 1 over 10 comes out, the ln of 10 comes out, so, and we take derivative of the x squared plus 1. So I know it's going to be 1 over, oh, there it is, 1 over x squared plus 1 times derivative of x squared plus 1, which is going to be 2x. So that's pretty simplified. The only thing I really have to do is, if you want, I say it's just 2x over ln of 10 times x squared plus 1. Now they're getting a little bit harder still. So for the next part, I'm going to zoom in a little bit here. I'm going to rewrite it again in a way that we can manage it. So I'll just rewrite it up here a little bit. So that's the same thing as saying the ln of x squared times 2 to the exponent x over the ln of 2. So, excuse me, if I do my first derivative, the derivative of, so we know we have the 1 over the ln of x, ln of 2, which is our constant. The derivative of ln of x squared times 2 to the x is 1 over x squared times 2 to the x times derivative of the numerators, or it's not the numerator, the x squared times 2 to the x. So it'll be 2x times 2 to the exponent x plus x squared times derivative of 2 to the exponent x is going to be ln of 2 times 2 to the x. So I'm just looking for something we can simplify. We can take out a 2 to the exponent x. We can take out one of the x's. Let's see where that takes us. So if I do that, what I'm going to have is f prime of x is equal to 2x, sorry, not 2x, just x times 2 to the exponent x. And what that leaves us on the numerator is going to be 2 plus the ln of 2. Now in the denominator, we're going to have x squared. So we have ln of 2 times x squared times 2 to the x. Now the 2 to the x can cancel each other out. One of the x's cancel each other out. And then we get our final answer, which is going to be, I'm not going to have any space there either, which is going to be f prime of x is equal to 2 plus ln of 2 over x ln of 2. I'm going to do the last one in a different color. It's getting messy, right? So once again, what I'm going to do is I'm going to convert this into something that we can work with. So I'm going to say it's going to be the ln of x over the ln of 10. So if I do that, I know that my 1 over ln of 10 is my constant. I can take that out. So if I do f prime of x, I have my 1 over ln of 10. Now the derivative of ln of x can be 1 over ln of x, right? Times derivative of the ln of x can be 1 over x. And that's going to be all over ln of 10, which I already have is taken out. And if we try and simplify that, not very much we can do there. So basically, on the numerator, we're just going to have a 1. On the denominator, it's going to be kind of tricky, right? I'm going to put the ln of 10 first times x times the ln of x. And that should be our final answer. Here comes the good stuff. Find the equation of the tangent line to the curve y is equal to e to negative x ln of x at point P, which is 1 and 0. Woof. So the first thing we have to do is we're trying to find the equation of the tangent line. So that means I take derivative. So here we go. F prime of x. And the derivative of e to negative x is basically e to negative x times negative 1, because we take derivative of the function, which is negative x, times the ln of x, plus we have e to the negative x times the ln of x, which is 1 over x. Now I gotta figure a way of cleaning this all up if possible. I really don't see a way of cleaning it up. I can probably factor out e to the negative x. All right, let's see if that helps. So if I do f prime of x, which is equal to e to the negative x, all right, and what I'm going to do is I'm going to switch the order because I want to lead with a positive. All right. In this case here, we're not looking for the slope of the tangent, so I really wasted my time doing that. I just had to put the value of x into the function that I wanted. So what I want is f prime of 1. And if I put that into my calculator, I get something that looks like 0.3679. So if I want to find now the equation, all right, the equation of the line, any slope-intercept form is going to be 0.3679x, that's my slope, plus b. And we have to plug in a point that we know for sure that's on that line. And the only point that we know is point P, which is 1 and 0. So if that's the case, we know y has to equal to 0, x has to equal to 1. That makes my calculation so much easier, right? So my 0 is equal to 0.3679 plus b, or b is equal to negative 0.3679. And we can write it together as a function is equal to 0.3679x minus 0.3679, and that's our equation of the tangent line at 1. For question number 4, it says find the local extreme for points f of x, which is equal to ln of x over x. So to find the extreme, we want to find the max or mins or critical points. We have to take its derivative, so let's do that. So I'm going to take the derivative of ln of x, which is 1 over x, times the denominator, which is x, subtract ln of x. Keep on doing that, ln of x, times derivative of x, which is 1, all over x, and we square it. If I clean this up, those cancel. So what I have is f prime of x is equal to 1 minus ln of x over x squared. Now, we have to find the critical points, so that means we have to set that equal to 0. So f prime of x is equal to 0 when, well, we're trying to set the numerator equal to 0, so we're going to have 1 minus ln of x is equal to 0, or ln of x is equal to 1. So we know that in this case here, x is equal to e, since ln of e is equal to 1. You can verify that in your calculator. So the next thing I think I got to do is do a chart to see if it's a maximum or min, or I can test values, right? But I think this is more of a chart type question. So, let's move that to straight. So I need one for x, one for f prime of x, one for x. So here we go. I think it should be enough. So we know this one's going to be e. This is when x is greater than e. And we know in this case here that this is when x is going to be less than e, but also x has to be greater than 0. It can't be equal to 0. So if we do our f prime of x and we do our f of x, right, we know that that's equal to 0 right there. And if I plug that back in to x, we're going to have ln of e over e. And for the next one, if I plug in a value, I'll do the greater than. If I do greater than e, so greater than 2.7, I'm going to get a value that's going to be negative. So it's going down. If I do a value between e and 0, let's say 1, what's going to happen? It's going to be positive, so it means it's going to be going up. Therefore, we can say that it's going to be a local max at e and 1 over e. Find the inflection points for f of x equals x squared ln of x. So what I'm going to do is I'm going to take the first derivative. So derivative of x squared is 2x times ln of x plus x squared times derivative of ln of x, which is 1 over x. We can see that one of these x's cancel out, and we get f prime of x, which is equal to 2x times the ln of x plus x. Now I'm going to take our second derivative. Derivative of 2x is just basically 2 times the ln of x plus 2x times derivative of x ln of x, which is 1 over x, plus the 1 at the very end. Once again, x's cancel out, and if I simplify this, we have f double prime of x, which is equal to 2 times the ln of x plus 2 plus 1, or f double prime of x is equal to 2 times ln of x plus 3. Let's make it look pretty. Now, f double prime of x is equal to 0 when we have 2 ln of x is equal to negative 3. I'm going to bring the 2 over to the other side by dividing both sides by 2. So we have the ln of x equals to negative 3 over 2. And now what I got to do is I want to cancel out the ln. So the way I'm going to do that is by using its inverse. It's going to be x is going to equal to e to the negative 3 over 2, or x is equal to, if we think about it, we have e. Maybe I should write it full out for you. Let's see if I have space. That's the same thing as saying x is equal to 1 over e to the 3 halves, or that's equal to 1 over e to the 2 over 2 times 1 over 2. It's kind of squished in there, which x is equal to 1 over e root e. I'm going to create a chart so we can see if it actually is a point of inflection. So here we go. I'm going to need a horizontal for that. I need another horizontal for that. Again, another one for that. Maybe I should move that down a little bit, give it some more space. Okay, and I'm going to create some more lines. I'm going upwards. Come on, there it is. We need one more and one more. Let's fill this in. So what I have is I have f double prime of x. I have f of x. I have my 1 over e root e. And what I'm going to do, well, I know that we solve for when it's 0 there, so for our second derivative, right? So that's that part there. And we know, well, I didn't calculate, but we'll calculate it later. So what I'm going to do is plug in the value that's less than 1 over e root e. And what we're going to see is that the value of the second derivative is going to be a negative, so it means it's going to be a concave down. And what I'm going to do is plug in a value that's greater than 1 over e root e, and what we're going to have is a positive. We're going to see it's concave up. So we can clearly see that at 1 over e root e, it's going to be an inflection point. So if I were to plug in f of e to exponent negative 3 halves, what I'm going to have, I've got it really small, it's going to be e to the negative 3 over 2 all squared times negative 3 over 2. And if we clean this all up, we're going to get negative 3 stays in the top. That becomes a squared. That goes there. And it's going to become 2e to the exponent 3. So therefore, our inflection point is going to be 1 over e root e and negative 3 over 2e exponent 3. So let's put that in there. 2e to exponent 3. Here's some cool ones. This is a good test type question. So we have y is equal to x to the x. So this is something that we haven't seen, so I'm going to have to use a different trick, right? What I'm going to do is I'm going to take the ln of both sides. And now that I do that, I can actually drop the exponent. So when I drop the exponent, I have x ln of x. And now I can take the derivative. So if I take the derivative, if I take its derivative, it's going to be 1 over y times dy dx. And that's equal to 1 times the ln of x, derivative of the x times the ln of x, plus x times derivative of ln of x. All right? And we can simplify. My screen's out of control. So it just becomes just 1. If I clean this up, we have 1 over y times dy dx is equal just to ln of x plus 1. Now, the goal here is to get rid of the 1 over y. So what I'm going to do is I'm going to multiply this side by y. Whatever I do to this side, I do the same thing to the other side. So if we think about that, the y's will cancel out. And what we're going to have is our dy dx, right? And we have y times the ln of x plus 1. We really can't leave it that way, right? But we know that over here, that y is equal to x x exponent x. So I'm going to replace it. So our dy dx, or our derivative, dx, is equal to x exponent x times the ln of x plus 1. And that's our final answer. And the last one, another good type of test question. In this case here, we have an absolute function. So we have to break it down into two parts. So we can say that y is going to be ln of x, where x is greater than 0, and ln of negative x, where x has to be less than 0. Okay, ln of x can never be 0. So if I take its derivative, right, if I do y prime, the ln of x now just becomes 1 over x, right, for where x is greater than 0. And our ln of negative x is going to be 1 over negative x for when x is less than 0. Sorry, I forgot to do one more thing. So that's that part there. Times I have to also multiply by derivative of negative x, which is negative 1, which is going to give me just really 1 over x when x is less than 0. So what are we looking for? We're looking for the derivative. So we're going to say that in this case here, y prime, since it's equal to both the same thing, 1 over x over here and 1 over x over there, we're going to say that the derivative of the ln of the absolute value of x is equal to 1 over x for the condition where x does not equal 0. And that's it for this lesson.